So in the last video, we gave a brief introduction to what a matrix is, a very loose introduction, and pretty much only one application of how we use matrices, which is we can use them to represent systems of equations, and maybe in the near future it will be easier for us to solve systems of equations using matrices. It'll be an easier way for us to keep things organized than just writing down systems of equations. And we talked about coefficient matrices, and we also talked about the augmented matrix, and that's pretty much where we left things off. So this video is going to cover basically a substantial amount of information regarding, how we refer to matrices and some kind of overarching goals of things we're trying to achieve when we're working with matrices. So the very first thing we're going to talk about is what we mean when we talk about the dimensions of a matrix. So usually we'll say, let A be what we call an M by N matrix. Okay, so A is basically just the name of our matrix, and the idea is that, then the matrix A has M rows, and N columns. Okay, and that's super useful for us. So, for instance, the matrix 1, 2, 3, 4, 5, 6, right? If this is our matrix A, then we might say this is a 2 by 3 matrix, right? It has 2 rows and 3 very clear columns. Okay. Some other things that we want to know about is what we call a leading term or a leading entry. So a leading entry is the first non-zero entry in a particular row. So non-zero entry in each row of a matrix. So, for instance, in this particular one the example I gave above, the number 1 is a leading entry in the first row. The number 4 is a leading entry in the second row. But if I had replaced, say, this first value here with a 0, then the first leading entry in the second row would be this 5. Okay. So leading entries are going to be very useful for us because they're going to have to do with this thing called pivots, pivot rows, pivot columns, pivot positions that we're going to talk about here pretty shortly. Okay, so from here we're going to talk about maybe some classifications of matrices. So we learned about the coefficient matrix and the augmented matrix, but specifically we're going to be talking about certain ways that a matrix may be represented. And what I mean is, for starting, a regular matrix, just a regular random matrix, might look something of the form, I don't know, let's write a few varieties. So 1, 1, 1, 0, 2, -1, 0, 0, -1, 3, -1, 8. So this right here is a 3 by 4 matrix. Maybe another one we could come up with might be 1, 2, 3, 4, 5, 6, 0, 7, 8, 9, 10, 11. Maybe there's 0, 0, 0 down here, right? We could make one like this. And this one has 1, 2, 3, 4, 5 rows. So this is going to be a 5 by 3 matrix, okay? And so these matrices, they're just random matrices, and kind of depending on if these are coefficient matrices or not, would tell us how many variables we have. So for instance, if these are all coefficient matrices, then this first column here is x1, that's x2, that's x3, that's x4, this is x1, x2, x3. If these are augmented matrices, then we have the x1 plus certain x2 plus certain x3 is equal to these numbers, and here we'd have some x1, some x2, add them together, and we get the numbers on the right. So it kind of just depends on which ones these are. But for now, I'm going to say it's irrelevant. Just they're 3x4, 5x3 matrices, and that's it. Now, when it comes to solving problems, solving systems of equations using matrix algebra, one of our goals, one of the forms that we want to get our matrix into is what we call echelon form. Okay, so the echelon form of a matrix is basically a point at which solving our system becomes possible. So is the first point when solving our system, or when solving the matrix, becomes possible. And I'm going to give you some visual examples of what some matrices in echelon form look like, and see if we can kind of come up with some general kind of guidelines about it. So, for example, a matrix in echelon form, let's see, might be of the form 4, 7, 1, 0, 0, 0, and I'm making these all up very randomly just to give you just some just a little bit of variety in what you're writing down, probably for your notes. But something like this, that's in echelon form. Let's see, something like 1, 1, 1, 0, 0, -3, -2, 0, and 0, 0, -2, 6. That's in echelon form. Maybe we'll do one more as well. Let's do 1, 1, 1, 0, 0, 1, 0, 2, and then let's do 0, 0, -2, 6. Okay. So these are all matrices in what we call echelon form. And the idea here, what makes a matrix be in echelon form versus maybe one of these seemingly more random matrices up above, is this matrix is just a random hodgepodge, system of equations of sorts. But you might notice that this one, if we look at, say, like the last row, if this is a coefficient matrix, then we're going to have 5x5 is equal to something, and maybe we can start actually solving this thing. In the last one here, it's going to take a little bit of practice, so don't worry if you can't recognize it right now, but this last one would be like -2 times x3 plus 6x4 is equal to something, and you might be like, well, Dylan, we can't really solve this, and like, yes and no, turns out that we can work with this still, but the idea is that I can't really manipulate this anymore to get into like a more solvable state, so to speak. Like I can actually start working with this right away. And so there's a classification for what it means to really be in echelon form. Okay, so there's 3 rules. So for echelon form, the rules are as follows. So number 1, so all non-zero rows are above any rows of all zeros. Okay, that's the first rule. Number 2 is that each leading entry of a row, so each leading entry of a row is in a column to the right of the previous leading entry. Is in a column that's to the right of the previous leading entry. Shorthand this as LE, leading entry. Okay, in the row above it is what I mean. And so you might notice that in all of these examples, the first leading entry here is right here, and the next one goes 0, 0, and then we have the next leading entry right here. And notice that it is in a column that is to the right of the previous one. And if we drop down to the next row, it's 0, 0, 0, 0, and then we have the next leading entry right there. If we go to the next one, we have 1 here. The next leading entry is -3, the next leading entry being -2, etc., and then 1, 1, and -2. So you'll notice in the original regular matrices, the leading entries that we have, they're all, these are all non-zero leading entries, and they're all in the same column. So that's like an immediate dead giveaway. This is not an echelon form. Okay, you kind of just get like this pattern where you have numbers with a bunch of zeros everywhere else, kind of that come before them, and they kind of create this diagonal sort of pattern, which we'll start to pick up on a little later in the class. Okay, and so then the last condition, as promised, condition 3, is that all entries in a column, so all entries in a column below a leading entry are zeros. Are zeros. Okay, and so that's the pattern I was alluding to, that we have zeros here, we have 0 here, I have 0 here, I have 0 here. Right? All the entries below our leading entries have to all be zeros. Now, what that means here is that maybe a good question to ask is, well, then could I have numbers here? Could those be could I have numbers there? Would it still be in echelon form? So what happens? Let's try it. If I replace this with like the number 1 and 2, do I still have echelon form? And the answer is no, because now our leading entry in the second row moves. This becomes our leading entry, but unfortunately we don't have a 0 under it. So this is not quite in echelon form yet. Okay, so this is one particular form. I'm going to talk about the next form, and then I'm going to talk about why we care about these forms. But the shorthand reason is that getting a matrix from something that looks like a complete hodgepodge of numbers into something that's a little bit more structured will end up being a lot easier for us to solve and to really start seeing the bigger picture for various applications that are going to happen in the future. So echelon form looks like this. We have one more, and it's called reduced or row reduced echelon form. So row reduced echelon form comes with 2 more restrictions. Okay, and so I'm going to label them as 4 and 5. They're kind of like, there needs to be echelon form and then two more conditions. So the first condition is that those leading entries need to be 1. Okay, the leading entries need to all be 1. Oops. The leading entries need to all be 1. And the last condition is simply that each leading entry, aka R1, is the only entry in the column, or the only non-zero entry in the column. It's the only non-zero entry in the column. So how would I have to modify some of the ones above? Let's take a look, say, at this matrix right here. I would have to have given you something that looks like, so the definition is that I need all of our leading entries. So this one, and this one, they all have to be 1s. So that means we're gonna have to change this one to be a 1. That would have to be a 1. And then every other entry in the column is going to also have to be a 0. So I'm going to have to replace those with zeros. Now, I'm just doing this just to show you this is a matrix that would be in row-reduced echelon form. You might be saying, okay, well, do I have to have 1s here or zeros here? What's the deal? And the answer is no, right? We have an echelon form. We've satisfied all of the conditions requiring us to have 1s in these leading entries, zeros above and below all of them. We have done our job. This is as good as it gets. Okay. And so I'm just kind of making them up as I go. But there will actually be real row operations and things kind of that we alluded to in the last video, where when we manipulate these matrices, we're going to try to get it into row reduced echelon form. That's going to be our goal. So at the very beginning, row reduced echelon form and echelon form tends to be a little intimidating for people. So I'm just going to kind of walk us through maybe a worked out example of what the heck it is that I'm going on about. So for example, maybe I start off with a matrix that's already in some sort of form, and let's see if we can identify what kind of form this is. And let's say this is an augmented matrix. So let's say we have 2, 2, 2, 4. Maybe the next line is 0, 1, 7, 8. And then the last one is 0, 0, 7, 5. Okay, now if this matrix represents a system of equations, what we really have here, just as a reminder, is that this first line is 2x1 plus 2x2 plus 2x3 is equal to 4. The second row is we have 1x2 plus 7x3 is equal to 8. And the last one says that we have 7x3 is equal to 5. And we could actually go ahead and solve this system because this one tells me how to solve for x3. Once I have x3, I could solve for x2. Once I have x2, I could go ahead and solve for x1, and I could finish this problem. But right now, that's not the goal of this exercise. The goal of this exercise is simply going to be to identify whether this matrix is in any of the forms that I just mentioned, and if it's not, can we get it into one of those forms? So it turns out that this matrix, let's see, it has some leading entries, and fun fact, these leading entries right here, this one that I'm circling, that leading entry here, and this leading entry, these have a fancy word. Instead of continuously calling them just generic leading entries, these are actually what we call pivots. Okay, and pivots in a matrix will eventually become ones in row reduced echelon form. So we shorthand row reduced echelon form as RREF. And sometimes we refer to these columns that they're in as pivot columns. So these three here are all pivot columns because they each contain a pivot. Fantastic. And so maybe just to kind of go back to one of the ones up here really quick. So if we take a look, say, at this matrix right here, it turns out that these leading entries that I have circled here, those are the pivots. That's a pivot, that's a pivot, that's a pivot. Provided I actually have this in in echelon form. There we go. So those are all pivots. Let me kind of erase some of the extra stuff that I have written here so it's a little more clear. Okay, try and use the same colors. So 0, 0, okay. So that's a pivot, that's a pivot, and that's a pivot. And then each of these columns, this column, column 1, column 2, and column 5 are pivot columns. Okay, and everything else is just kind of generic. So going back to this example that we're working on down here, the goal is to identify what this is. And it turns out this is already an echelon form. It's an echelon form because if we maybe zoom out to the rules, so we just kind of go through our checklist, right? So are all the non-zero rows above any rows of zeros? Well, we don't have any non-zero rows, so that's an easy check. Each leading entry of a row is in a column to the right of the previous one. That's correct, because all of these leading entries, they go in this diagonal pattern, which means they're all in a column that's to the right of the previous leading entries, or the previous row's leading entries, so that's good. So check mark there. And then all entries in a column below a leading entry are zeros, and that is true. We have zeros here, we have zeros here, and there's nothing below the 7. So this is actually already in echelon form, so check mark. And so our goal here is going to be to, just for the sake of showing you something, that what I want to do is I would like to turn this into a row reduced echelon form. So my current goal is to turn this matrix into row reduced echelon form. Okay. And so there's a strategy to doing this, and the strategy is going to be the following. So in every single matrix that you're going to tackle, this is an approach I use. Now there are different approaches for how to go about figuring out the row reduced echelon form of a matrix, but this is the approach that I take. So the first thing that I know is that since this is my first pivot, I'm going to put a circle around it. And I know that for row reduced echelon form, that needs to be a 1. So the very first thing I'm going to do is ask myself, okay, well, what operation do I need to do to this matrix in order to turn that into a 1? And before we even do that, we have to think about, what are the row operations, right? What can we actually do to matrices and what can't we that makes sense? This is actually not too hard to think about because, and I'm just going to kind of make an aside here. And this aside is going to be, what row operations can we do to a matrix? What row operations can we do to a matrix? Okay. It turns out there's not really that many because remember, this is a system of equations, right? This is secretly the system of equations 2x1 plus 2x2 plus 2x3 is equal to 4. It's x2 plus 7x3 is equal to 8. And it's also 7x3 is equal to 5. So if you were to try and answer the question, what can or can't I do to this system of equations, there's not that many things. The first thing that we could do is I could multiply a row by a scalar. Multiply an entire row by a scalar. Okay, so that means if I decide to multiply the top row by a half or by 10 or whatever, it's not going to change the solution to this system. And, case in point, if I have x equals 2 and I multiply both of these sides by 10, I'd get 10x equals 20. The solution is still x equals 2. Just by multiplying by 2, I haven't changed anything. It looks different, but it's still going to give you the same answer, so that checks out. What else could we do? We found out that I can add rows together or subtract rows, and I can create new rows from that. So the second thing that we can do is we can add and subtract rows, to create new equations. Okay, that's something we can do. And then lastly, the third thing that we can do is it doesn't really matter the order that I write any of these in. I could swap the row positions at any time. And that's pretty much it. So you can swap row positions at any time. Okay, and those are going to be those three things are going to be our guiding principles for what we can and can't do to this matrix when we're trying to get it in this mysterious, magical, what we call row reduced echelon form. And so what I'm thinking, right, is my very first step here is I would like to replace this 2. I want to replace this 2 with a 1 because it's my first leading entry in the first row. It's in the upper left-hand corner of the matrix. I want this to be a 1. So my goal is, at this point, I'm going to scale that entire first row by 1/2. And the way I'm going to write this down to keep track of it is I'm going to replace my row 1. So I'm going to create a new row 1, and it's going to be, how am I going to get it? I'm going to take 1/2 and I'm going to multiply it by the existing row 1. And that is going to give me a new matrix where I have 1, 1, 1, and then at 2, then I have 0, 1, 7, 8, and then 0, 0, 7, 5, like so. And the nice thing at this point is I have a 1 here, and I have zeros above and below it, right? And so we are kind of, check mark, we're on our way. So we go on to the next row and we identify, okay, here's another pivot, right? There's the next pivot. That's really nice. But for it to be in row reduced echelon form, not only do I need a 0 below it in this column, I need a 0 above it in the column as well. And so there's some different things that we can do, but maybe one thing that comes to mind is if I take the first row and I subtract the second row from it, that will create a new row that has a 0 right here, because last time I checked, 1 minus 1 is equal to 0. So what I'm going to do now is I'm going to take row 1, and I'm going to create a new row 1 that I'm going to get from taking row 1 and subtracting row 2 from it. And so this is going to get me the matrix. Let's see, 1 minus 0 is a 1, so there we go. 1 minus 1 is 0. Now 1 minus 7 here, that's going to be a negative 6. And then we get 2 minus 8, that's going to be a negative 6 as well. And then the second row stays the same. We didn't mess with that at all, and we didn't mess with the third row at all either. But now we have successfully accomplished the second part, which is I have my pivots here, and there are zeros above and below each of them. So we're going to move on to, of course, the last one, which is going to be this 7 right here. The very first thing that we're going to need to do to kind of finish our little excursion here is I'm going to need to turn that into a 1. And so how am I going to do that? I'm going to take row 3. I'm going to create a new row 3. And I'm going to get it by just scaling everything by 1/7. You can think about it as dividing the row by 7 if you want. But I'm going to scale row 3 by the coefficient of 1/7. And that's going to give me a new matrix where that third pivot is now a 1. So the first two rows should stay exactly the same because we have not done anything to them. So that's still 1, 0, negative 6, negative 6. We'll have 0, 1, 7, and 8, and then 0, 0, 1, and 5/7 right here. And we're almost done at this point. The last thing that we need to do, of course, to get this into row reduced echelon form would be to take this 1 and use it to kind of obliterate the 7 and the negative 6 above it, turn those into zeros. That's basically the general strategy. And at this point, I'm going to kill two birds with one stone in the sense that I'm going to replace row 2. My row 2 I'm going to get by doing the following. If I take the existing row 2 and I subtract 7 of row 3, right? So the idea basically being that if I were to, off to the side somewhere, take this row, multiply it by 7, I would get 7 and I'd have 5. And then I could subtract this 7 with this 7, and that's going to give me a 0. And you might be wondering, okay, but if you do that, isn't your third row going to be different? You could just imagine that I multiply this by 7, I do the operation, and then I multiply it by 1/7 again to get right back to where we started. The whole point being that I can just take row 2 and subtract 7 of row 3 from it, and that's going to get me a new row 2. That's exactly what I'm looking for. So what do I mean? If I operate on this thing, I have 0, 0, 1, and 5/7. My row 2 now is going to become 0, 1, 0. Now I have to remember that I took row 2, which is right here, row 2, and I'm subtracting 7 of row 3, which means I'm going to get a 3 in this spot, right? Because if I take this, and I do 8 minus, and I do 7 times row 3, that's going to give me 8 minus 5, and last time I checked, that is indeed 3. And so in the first row, I'm also going to do something to it, and I'm going to replace the first row with something new, and I'm going to take row 1, and I'm going to subtract, or add in this case, I guess, let's see. So I have a negative 6, so I guess if I multiply this by a positive 6, and I just add it, if I add row 3 to row 1, then I should get something good. So let's take row 1, and I'm going to add 6 row 3 to it. And so if I do that, I'm going to get 1, 0, 0. And so the only operation I really need to worry about is the fact that, okay, I'm going to take negative 6, and I'm going to add 6 of my row 3 entry there, right here. And that's going to be something not very fun. So what am I going to get? I'm going to get negative 6 plus 30 over 7. So if we get some common denominators really quick, that's going to become negative 42 over 7 plus 30 over 7. And that should leave us negative 12 over 7, like so. And this is our row reduced echelon form. Okay, this is row reduced echelon form. We have accomplished what we set out to do. And so this is useful for a couple of reasons, okay? The first reason why this is useful is, number one, now I know, remember that this is my x1 column, this is my x2 column, and this is my x3 column. So now I immediately know exactly what x3 is, x2, x1. I'm done. I immediately just get the answers for free, whereas in the original one, just by looking at it, even though, yes, there's some things we could do, and we could do a whole bunch of back substitution, we don't have the answers just staring at us in the face. So that's like the first, one of the most important reasons why RREF is like the nicest form of any matrix if we can get there. The second reason is that the row reduced echelon form of a matrix is what we call unique. So what does that mean? That means that if I took the matrix that we started with, 2, 2, 2, 4, 0, 1, 7, 8, 0, 0, 7, 5, if I were to multiply everything by 3, just for the sake of doing it, I could create a new matrix. So let's say if this is called my matrix A, I could create a new matrix B that looks like, I don't know, let's just, multiply everything by 3. So let's say, so like 6, 6, 6, 12. And let's do 0, 3, 21, 24, and 0, 0, 21, 15. Both of these matrices have the exact same answer. Even if I only multiplied the first row by, let's say, 10, so I had 20, 20, 20, and 40, and then I had 0, 1, 7, 8, and 0, 0, 7, 5, right? All of these matrices look starkly different, right? They all look completely different, but it turns out they're what we call row equivalent. So all of these matrices are what we call row equivalent. Row equivalent. And the idea is that all three of these matrices, they reduce down into this particular RREF, right? They reduce down into that exact same matrix with the ones in the diagonal and then some numbers at the end in this particular case. So even though they all look very different, that's what they simplify down to. And that's like a key takeaway with row reduced echelon form. The idea is just like back when we did algebra way back in the day and we had 2/4 and 3/6 and 50 over 100, all of these fractions, 50 over 100, all of these fractions are the exact same, but it turns out that the easiest fraction that we use to represent all of these is 1/2, because 1/2 is the most reduced, simplest, easiest form to use. Now, it's not to say that these don't have a purpose. It's just that if you were to ask somebody, are these all the same? If they didn't have any practice in algebra, they might say, no, they don't really look the same, or maybe they are, I don't know. And they would try and go and do their simplification until they eventually realize that when you simplify all of these, they all still end up being 1/2. So that's like the big takeaway between taking a matrix that's just a gobbledygook of numbers and trying to work it into its row reduced echelon form. Echelon form is cool, right? Echelon form is just fine for starting to do some solving stuff, but row reduced echelon form is kind of like the form that we want, where we're not going to make any mistakes, we're as simplified as possible, we're looking at the bare bones of the system, and we can get some information out of it.